keynote lecture of the conference. My pleasure to welcome Seth Lloyd of MIT. He will speak on space-time as quantum computation. Thank you.
Great. Thank you very much. Good. Up and down there. Great. Do I need a microphone? I'm pretty loud. I think that people can probably hear it.
Yes,
Unless you want to be recorded. Here we go. Okay. It's a real pleasure to be at this conference. I've tried to come to this conference twice in the past and failed both times. Most recently because it was postponed for several years. It's a great pleasure to be here. This is a wonderful conference, and I've heard about it from my friends many times. And I'd like to thank Thomas in particular. We haven't seen each other since a conference that Vortex Zurich organized in Santa Barbara in 1994. I should also mention I got a note from the editor of Entropy last night. Sorry, of Entropy, who's Entropy is sponsoring this keynote lecture, and I'm also one of the quantum information editors, maybe even the quantum information editor at Entropy. And I encourage you to submit your papers to Entropy. I guarantee as an editor that papers from people at DICE will be treated with special tenderness and care.
you give us a good rejection, maybe.
Yeah, that's right. Very pleasant rejection. That's right. Okay, so I will tell you this. I'm sorry, I think I should do this. Stand up, Jeremy. Let's see what it looks like here. This work that I'm going to tell you about is really exciting for me to talk about this because, in fact, the idea of space-time or quantum gravity as a quantum computation is something I've been working on for a very long time. I dread to say how many decades, but you'll figure out in just a second. I entitled it Space-Time as Quantum Computation, but now I note that I can actually, the times have caught up. And so because a quantum computation is in fact a tensor network, I can now refer to this as a talk about quantum gravity as a space-time tensor network, which sounds very trendy under all the current foofara from the ADS CFT community about tensor networks, etc. Okay, so let me, since I actually have slightly more time than some other speakers, I'm going to indulge myself by telling a little story. So in 1984, showing you how many decades ago it was, I was doing my MPhil at Cambridge with Jeremy. Jeremy very kindly, I approached Jeremy and said, I never really understood all this stuff about electrons being in two places at once and entanglement, and he kindly took me on as a graduate student and let me work on ideas about information in quantum mechanics. This was before there was a field called quantum information theory. And he also, Jeremy had a very wonderful weekly seminar about what we would now call quantum information, about foundations of quantum mechanics, entanglement, etc. And it was great. And he also pointed me to all the literature, a lot of the literature. I read a great deal. It was a wonderful experience. And indeed, that's what decided. It was so great that I decided to do a PhD on the same subject, whereupon all my papers were immediately rejected because it was a subject of no interest to people at that time. However, at the same time, in spring of 1984, having done Part 3 maths and studied general relativity in many guises, I took Stephen Hawking's course on quantum gravity. I would like to relate the following event that happened during this course. If Jonathan Hallowell were here, then he would confirm, he was at this event, and he would confirm what I'm going to tell you now. Unfortunately, he is not. He sends his regrets to everybody. He is suffering from long COVID, and I suggest that anybody who should drop him a note to tell him how much that we miss him here. I'm sure that he would appreciate it. All right. So now, so picture yourself in the old damp on Silver Street in Cambridge, and there's a kind of musty old lecture hall with like seats going up, and just like here, there's a dais, a stage in front. And Stephen Hawking is sitting on his wheelchair on the stage. And this is his quantum gravity seminar, so he's reporting on works that he's just interested in and working on at that time. And so, now back at that time, Stephen could still speak, but only a few people could understand him. So the way the lecture went, and he couldn't write on the board or anything, the way the lecture would go is Hawking would say something, and then this postdoc, who was a rather foppish young man wearing a pink coat, would say, Professor Hawking says, this lecture is about the edge of the universe. The edge of the universe is very far away. But we can picture it like this. And then he drew a picture of the time that you'll be seeing later on during this talk. It's like this. Here is a Penrose diagram for Minkowski space. We'll talk about Penrose diagrams into this. And then this goes on. So, we can, by doing a conformal transformation, we can bring the infinite light boundary of Minkowski space into a picture we can draw on the board. And so it went on like this. It was very fascinating. Hawking was a very clear and excellent lecturer, but perhaps the most important thing was everything had to be said twice. And that gave you time to take notes. So it went on, and he was talking about things that interested him at the time, about quantum cosmology, and while the postdoc was writing on the board, Stephen had nothing to do. So, because he was, agitated, he would fidget. And because the only way he could fidget was to move his fingers, and so while the postdoc was writing, he would move his fingers on his wheelchair, and the wheelchair would go, Well, everything was fine until about, 45 minutes into an hour and a half lecture. While the postdoc was writing, there was a tremendous crash, and Hawking and his wheelchair had fallen off the dais, and he was running with his legs wiggling in the air like this. And so, oh my God! And I was sitting in the front row with some people. We went and we picked him up and we put him back onto they were sitting shaking with, oh, he's going to die right now. This is so horrible. But then after a while it calmed down, and it turned out that he was shaking with laughter. It was completely okay. And then after he kind of stopped laughing, he said, and the postdoc said, Professor Hawking says, fell off the edge of the universe. Inspired by Jeremy and by Stephen, I subsequently spent, now it's almost 4 decades, and a year or two, exploring the notion that we might be able to understand ideas about quantum gravity via looking about quantum mechanics and information, notions of correlation and entanglement. And indeed, a number of years later, I started working on quantum computation, and I realized that quantum computation was probably a pretty good way to try to explore how quantum information gets processed in the universe, and might be able to give a reasonable theory of quantum gravity. And that's what I'm going to tell you about today. And I would say that this is not, in any sense, a closed field. I'm just going to make remarks for things about results to explain to you the basic idea. But it's open-ended. And there are many different ways that one could try to work on this, and I will try to suggest different ways that are possible. It's an accessible way to talk about quantum gravity, because quantum computing is much easier than quantum gravity, as the debates of the last few days have indicated. All right, so let's go and see. Let's do this. So one of the points that Hawking brought up in another lecture here was the following. So he noted that the light cone, or the causal structure of spacetime, determines both the topology of spacetime, of the global spacetime and the local spacetime, and it also determines the geometry of spacetime. So it determines the connectedness structure, the topology, and the geometry, the distance structure, but only up to a local timescale or conformal factor. And I've drawn a picture here to show how this works, to make it in a kind of discretized fashion why this is the case. These here are the light cones. I'm doing this in 1+1 dimensions due to the constraints of this medium. Probably on Twitter I could do it in many dimensions. But the light cone structure contains no information about the time. It just tells you what the causal structure is. And that actually already gives you a great deal about the metric. And if having drawn these little causal diamonds right here, you see that if you actually if you can determine what the proper times are in these directions, time of course always goes up in quantum gravity. I always like this. For engineers, time goes from right to left, and for physicists it goes from left to right, but in quantum gravity it goes from bottom to top, which is a hopeful way, I feel, of looking. It's like a tree growing up. It's a hopeful way of looking at the universe. But you see, just for this little piece right here, sorry, there. So I got to get my finger on the pulse. So if I set up these causal diamonds, and if I determine the length of the temporal length and proper time of these causal diamonds, then actually in this 1+1 dimensional picture, I've actually determined in a discretized fashion, for instance in Reggie calculus, the full geometry. So for instance, if I were to shorten this time right here, if all these times were equal, then I would have something that's flat. If I were to shorten this amount of time right here, that would induce curvature, because in fact, this surface would curve like that and develop positive curvature because there would be a deficit angle at this central point right here. Okay? So this was the starting point of my thinking about this. And are there questions about this? I would like to take questions during the talk, if possible. So, and it also holds in 3+1 dimensions or in n+1 dimensions. So it's just a nice fact about general relativity. So my take on this is the following. It's rather simple, actually. This is if I can get across this basic idea, I'll be happy. Yeah.
Since you asked, could I interrupt something? This picture is not background independent, I suppose, because you use coordinates somehow, or you can make it.
No, actually, everything. This is completely invariant under diffeomorphism invariant to all observers, because this is the proper time, right? That's why, so all observers, everybody agrees on the proper time and everybody agrees on the light cone, independent of what diffeomorphism you apply or independent of your frame of reference. Does that answer your question?
Yes.
No, it's not really, because proper time does depend on the metric frame. So if you make field transformations that change the metric, for example, in the theory, this metric in scalar fields, proper time will depend on it.
I don't think that if we regard this as if we regard this as a light cone and observers agree on this event and they all agree to call proper time as a scalar quantity, so they agree on the proper time.
Of course,
yeah,
but it is not invariant under field transformations.
Well, we have no field. We have
some people call in cosmology change of metric frame or Weyl transformations.
Yeah.
It's not invariant.
Certainly it's not invariant under Weyl transformations, because that would change the formal factor. That's in fact the whole point here, right? I mean, that's like, that's, I believe you're agreeing with me, though you expressed it as a disagreement. So I'll go on.
I agree with you.
Okay, now let's introduce the quantum computation, which now we're going to find out how might we determine these proper times. Okay? Now the idea here is that this is a very simple idea, is that a quantum computation has a causal, it has a light cone structure. Here's time going up. These lines indicate where quantum degrees of freedom which can interact with each other. So once again, we have time going up like this, and these two degrees of freedom interact via a quantum logic gate, which is a tensor, which is why this is a tensor network. It happens to be a unitary tensor. And then quantum computations have a causal structure. All right. And in addition, they have more. They have also an internal structure with interactions with the internal quantum degrees of freedom, which are given by these quantum logic gates. So the idea here is that we're going to try to reproduce. We could use the quantum computation, for example, to try to reproduce the dynamics of the underlying fields, the fermions, the bosons, the gauge fields, etc. And this is what you see, most of what I do is quantum computing, including building quantum computers, and I realize that I should have, my co-CEO will kill me if I don't point out that this is being done, I'm at MIT, but also at Turing, which is our company, was just trying to design applications for near-term quantum computers. We are hiring. Even if you do quantum gravity, we're hiring. So you see here there's a feature. We know that this is, I started working on quantum simulation as a result of teaching the undergraduate control theory laboratory in mechanical engineering at MIT, and with these beautiful analog computers, and I started saying, well, what would a quantum analog computer be? And Feynman had written something about this, but he didn't say how to do it. And so I said, oh, we could do this with a quantum computer. So in fact, as a result of that work, you can show that you could reproduce lattice gauge theories, fermions, etc., via a suitable quantum computation. So this actually is a sufficiently general structure to include what we see in ordinary quantum fields. But let me note something about this, that the variables that determine which quantum computation you are performing after you've given the circuit diagram, which has a causal structure, the variables that determine it are these times, these proper times, tau 1, tau 2, tau 3. And by writing this e to the minus h tau, what I really mean is I wish to have this be, again, be a scalar quantity. So really this is h tau, this is h in the, if you like, in the rest frame, which is just p mu tau mu. So this again is a scalar quantity that everybody agrees with. But note that the dynamics that is determined by these taus, this completely determines the computation once you've fixed, say, a particular kind of quantum logic gate. It's quite arbitrary which ones you pick to have universal computation. These are actually the same taus that appear here. So once you fix the causal structure, the same variables that are going to fix the actual geometry are also the variables that fix the computation. So the only variables in this field are in fact these proper times. And now we're going to look at what happens when we look at different possible quantum computations or different possible geometries. In particular, we'd like to relate the computation to the geometry. Yes?
Sorry, are you assuming some kind of locality here in the sense that every gate is connected to another gate or only to a nearest neighbor gate? You don't have any wires going horizontally to a faraway gate.
Yeah, I mean, let's assume a geometry for the sake of it that has three spatial dimensions, and the degrees of these gates then connect states that are adjacent. So that, let's say the topology is the topology of Minkowski space, and the light cone structure is the light cone structure of Minkowski space, for the moment. Locally, at any rate. We'll talk about more global aspects later on. Yeah, so this is these are assumed to be spatially local. These are these light cones. These light cones here are ordinary causal light cones. So the topology is that of Minkowski space, and now we want to try to determine the geometry. Again, the local topology is that of Minkowski space. Did that answer your question?
Basically you just have nearest neighbor interactions between the gates.
Right, so we've discretized the system, but the idea is that if they interact via a logic gate or local, that's a local event that takes place within a particular causal environment. Yes?
Why is the H same in all of these boxes?
See, there's an interesting feature here, which is that if you, I can take any H that generates where if you start commuting the H with itself acting on different degrees of freedom, if it generates a full algebra of Hamiltonians, of permission operators, which is the typical situation, then this picture is universal. That is, I can construct any ordinary quantum computation simply by varying these times. So the H is actually rather arbitrary here. It shouldn't have excess symmetry, so of course if we want to put in things like the Dirac equation, then it should have local Lorentz symmetry, which is fun. Yeah.
So you also have a frame, because I see that you take tau as being a vector, and you take the scalar product with the Pauli operators.
Tau is just a proper time.
Yes, but
Yeah.
you treat it like a
Tau
vector.
mu does not exist.
I'm sorry?
Tau mu does not exist. We do not know what that is.
Tau mu?
Tau mu.
Oh yeah, so this is, the
Tau is fine.
yeah,
Tau is fine,
right,
but,
P mu and tau mu are frame-dependent quantities, but the P mu, tau mu is
what is
not.
tau mu? I mean, there's
If you
no
embed,
time is well defined, but
so okay, so if you embed this in, you pick your own coordinate system. Tau mu is tau mu in this coordinate system. Philippe picks another one. He has a different tau mu, but this is the same in your different coordinate systems. Yes.
But this is one general
Yeah. So
Can you repeat the question?
yeah. Isn't this really an analog computer because the taus are continuous in time? Well, in quantum computing, this is normally, actually, they are all analog computers in the sense that you apply pulses to electrons or like quantum dots or superconducting systems and you turn them on and off continuously in time. So it is analog in that sense. Yes. Okay.
So H in the box just acts in this box? Or
Yeah, sorry, excuse me?
the H in the box just also the box?
Yeah, to think of this, the quantum computation is a discrete countable set of quantum degrees of freedom that interact via quantum logic gates which act only on 2 quantum degrees of freedom. They could act on 3 or 4 that are just adjacent to each other.
These H are all different in the sense that they concern different boxes.
It should be.
Which H? This is
There's H everywhere, but all these H are not the same H.
well, yeah, they can be the same H. In general, if you want to do, for instance, say a Dirac particle, these will be the Dirac, local Dirac Hamiltonian.
Okay, but within the box. So this one will have within this box and this in this box.
Yeah, this is a discrete picture where I apply a unitary transformation to 2 degrees of freedom at this point.
So the point is we are performing the same transformation but with different parameters.
With different parameters, right. And it's a fact, which I'm not going to prove to you, but I mentioned that I can actually do any, if I fix the H, then I can do any, generically I can do any transformation, unitary transformation. If the H has symmetries, I can do any transformation within the irreducible representations of that symmetry group.
So that kind of operator allows us to perform a universal set of gates.
Yeah, this is it, right. So if I pick a random 2-qubit H, it's universal.
But
For
if the
example.
space-time structure is like this, and I would expect that the energy content, TBD content in each of the boxes are different. So I would expect that the H should
Yeah, absolutely. So let's actually look at that. So because I want to be careful to actually go through the talk, this is good that I'm happy that this is exciting interest. Yeah, but this is very important because actually getting this straight is yes. So the states. Whoops, sorry. This is about the next to answer your next question. But the state of the quantum degrees of freedom coming in here will be in general different from the state of those there. To answer that question. Okay. All right. So now let's go in greater detail of what's actually happening. Let me unpack this in an equation. Unpack this picture. So each of these. Now here we have. Suppose we have some initial state. I didn't draw it in the previous picture. And if we're looking for the amplitude for the quantum computation, I simply have this is the action of the first quantum logic gate, the action of the second quantum logic gate, up to the action of the nth quantum logic gate. And so I have an overall unitary time evolution, and this gives me an amplitude for evolving the state psi naught into some final state psi final. It's like an ordinary quantum computation. And let me now decompose this into, I can decompose each of the H's into its corresponding energy eigenstates, and I can just write this as a sum over the energy eigenstates for the first quantum logic gate, the second quantum logic gate, etc. They're all the same they're all the same energy eigenstates, except applied to particular set degrees of freedom. And so this then is equal to this right here, and there's no gravity in this right here in the blue and red. So now we'd like to actually add gravity to this picture. We'll do this in an extremely simple way. This is just the most obvious way to do it, and it's direct. By the way, so as I'm a professor, of mechanical engineering or quantum mechanical engineering. The dean calls me a quantum mechanic, which is why I'm allowed to charge such high prices. If your quanta are broke, we fix them. There are not so many of us around, and there are many broken quanta. So, so I'm going to do this in a very direct fashion. I'm not going to be bothered too much about, I'm doing this in an operational fashion. I'll make choices for this point that just work, are the simplest that work well, but there are other ways to do this. Yeah?
Yeah. How are you ordering the unitary terms?
Oh, how do you order it? Oh, that was in the...
The order is not unitary.
No, the order is given by this causal structure right here. Well, these commute with each other. These do not. These two commute with each other. These two do not commute with each other. So we start with the first, and we go on to the end until we get there. And there's an ambiguity in the ones that correspond to space-like separation commute with each other, and so they can be performed in different orders.
Isn't not corresponding to a distinguished foliation of your discrete space-time?
We set the causal structure. Let's take it to be locally like Minkowski space. We put this discrete set of quantum logic gates there, and that determines a causal order. And then this is well defined. We can commute things that commute with each other. All right?
Yeah.
Does that work? Okay, good. So what we're going to do is we have this amplitude. We're simply going to multiply this. This right here is the amplitude that corresponds to the computation, and we're just going to multiply this to E times the EISG as determined by these taus. And this is the Einstein-Reggie action because it's a discrete picture. So as we go back through what we had before, we just do Reggie calculus with these taus, forget about the quantum computation, we fix the taus. This is now a Reggie calculus. I drew it in 1 + 1 dimensions, but the same holds in 2 + 1 dimensions, 3 + 1 dimensions, etc. So we just supply this Einstein-Reggie action. All right? So that's going to be our method. We'll just try it out and see what happens. Okay? I'm just, again, this is a kind of an engineering approach to quantum gravity. Right? Actually, by the way, engineers are, in some sense, it's a pleasure to work with them because like, my first class I taught, I was co-teaching with a senior person who was teaching classical mechanics, and he started off by saying, everything I'm going to tell you today is a pack of lies. And it's the same for the next lecture, but they're very valuable, useful lies that work extremely well when we're trying to, say, control a motor. So that's my attitude here. It may set me apart from you, but Murray Gilman, my postdoctoral supervisor, used to say, the way you make new discoveries is not by thinking of something new, but by discarding useless baggage. And so I'm just not going to worry about all the stuff that we've been worrying about so far. Who cares if the gravitational field, if the Coulomb forces, the Newtonian gravity is quantized? I don't care. Yeah.
Seth, since you mentioned Reggie, I was wondering how your formulation is different from what ambient Renata Lowe have been doing.
Oh yeah, it's quite different from like Renata. She builds up just pure gravity, right? With a set, when you have two different kinds of simplices, of four simplices, and you put them together, and then you get an action from that. But it would be the same action in that case. But this is clearly quite different because I actually have a whole bunch of dynamics as well as the gravity. Remember, we have degrees of freedom. The degrees of freedom are the proper times. They determine the metric, and they determine the computation. Okay, so let me go on.
Yeah, no, wait.
Yeah. So now let's actually.
But you see, they're doing quantum gravity, so they don't want to see time. I know you start out with time, and so my question is that do you end up doing something similar if you're willing to translate to each other?
Not really, because this really requires you to have dynamics on the system, the dynamics of the quantum computation. It doesn't make any sense to do this in the well. Okay, no, I think I can answer that. If I were to do just this with the Einstein-Reggie action and sum over the times, then I would be doing something like what Renata is doing. But I'm not doing that. I'm actually doing this and this.
Yeah,
okay?
But they have, you can interpret them as time steps.
Yeah, absolutely.
Forward. And in fact, that's how they concluded that the four-dimensional case is very difficult to find. You mostly find 2D. So
no, but okay, it's quite different in this case because I'm putting things down on a 3+1 dimensional manifold. I'm not trying to say the world is 3+1 dimensional. I'm saying this like the world is 3+1 dimensional. We live in de Sitter space, not anti-de Sitter space. So why should I study ADS-CFT? Anyway, so no, but so it is different from that. It's quite different. But let me continue with this rather than that. So because this, I think, is self-contained, and it gives, and also because if you don't let me continue, then I won't get to this point which you'll like, because let's now actually look at a path integral over all, over all possible proper times. And let's look at the stationary points of this path integral. So we're going to say the derivative with respect to a particular proper time of this amplitude should be equal to 0. And when you do that, then actually you simply get the expectation value of the jth Hamiltonian that corresponds to this point, minus the derivative of the Einstein-Reggie action with respect to this proper time is equal to 0. And this is just the time-like component of the Einstein-Reggie equations along this direction in the semi-classical Einstein equations. Yeah?
So when you sum over different histories, that include different tensor networks? Because
no, right now we're fixing the tensor network. We're only summing over different times. It's a very interesting question how you might extend this to sum over different possible tensor networks, which would be more like where Renata was talking about.
Because this means that you have a fixed causal structure and you only variate the density of the...
Exactly.
Yes.
Exactly. And looking at different, I'm just saying the causal structure is locally that of Minkowski space, which I think should be a relatively uncontroversial thing for most folks, those of us who live in Minkowski space, or for Einstein or something like that. So we'll look at the global structure later.
Yeah, so Seth, the reason why I asked you that question is actually trying to meet you at the end of your talk.
Well, you're not going to meet me at the end of my talk far too soon. So let me actually, let's talk at the end of the talk.
No, you want people to ask questions.
No, but I also want to get to the end of the talk. And I mean, notice that people are actually, I actually notice that many of these questions are actually comments rather than questions. So I'd rather, allow me to use my prerogative to continue.
I'm trying to replace quantum gravity by quantum computation.
No, I'm trying to derive a theory of quantum gravity based on quantum computation.
That's exactly why I asked that question.
What question?
I would hope that we let him go a little
Yeah, please.
To hear
Yes.
the rest of the talk.
Thank you, and if you promise not to say anything more, then I might make it. All right, so now let's look at what happens here, and let me now look what we get. So we get we just look at the stationary points, we get the semi-classical Einstein equations, which is nice, perhaps not very unexpected, because that's what happens when you take something like this, right? You basically have this is the derivative, this is the derivative, gives you the derivative with respect of the matter field action with respect to the metric, and this gives you the derivative of the Einstein-Reggie action with respect to the metric, and that's how you get the Einstein equations in the Hilbert formulation of Einstein equations. So now let's note here. So here's something quite important. This is the, I'm going to not take a few questions for a bit, because let's get to the stuff that people relate. I wrote this up to try to address things that people have been talking about throughout the last few days. So let me talk about those rather than you talking about them. And let's note here that actually this times and energy scales, these are the scales of ordinary matter. These are not necessarily the Planck time or anything like that. If we're trying to simulate something like the Dirac equation or the electron, then H is the scale of the electron. And the quantum fluctuations that we get around the semi-classical action are the order of the Planck scale. So what happens is that these proper times, which are on the scale of, say, strong interaction scale, these are much longer than the Planck time. So the fluctuations, the quantum fluctuations we get are actually Planck scale fluctuations. If I fix the tau, so if I fix a set of tau, for instance the semi-classical version, then the entire time evolution is unitary. This does not exhibit Penrose-Diósi decoherence or anything like that, or a Twift coherence or anything like that, but it does have, at a very small scale, you can get a slight amount of decoherence. Okay, so this is, several people mentioned this kind of decoherence, and that's what's going on here. So it's unitary for fixed tau, but we have a sum over different unitaries. Now they fluctuate with these proper times fluctuate at the Planck scale in this path integral. And so these are going to actually entangle or decohere matter and gravity at a rate of the Planck scale divided by whatever the, for instance, the strong interaction scale for each of these gates. So there will be a small amount of intrinsic decoherence in this picture. That's important, right? Because I mean, it's not fully unitary. I've talked with string theory and ADS-CFT folks about this, because they say, well, yes, because of the ADS-CFT correspondence, because the conformal field theory is exactly unitary, then quantum gravity has to be exactly unitary. But then, upon second thought, Lenny Susskind would say, well, maybe there are like little fluctuations, violations of unitary at this scale. So I think this is fine. This is kind of a sort of normal thing, but this is the kind of decoherence we get, gravitational induced decoherence we get. Yeah, it's easy. Great. So, and we can get decoherent histories over coarse-grained values of this energy momentum tensor. These are the hydrodynamic variables of Gell-Mann and Hartle. These are what Simon was talking about as a semi-classical frame, right? Is that the right words? Something like that.
Quasi-classical domain.
Quasi-classical domain. So there's an obvious and direct quasi-classical domain here, which are coarse-grained averages of energy and momentum over regions of space. So it exhibits decoherent histories. And now let's actually look at examples of terms in this Hamiltonian. We can do things like, you know, if these are fermions, let's say these are, for instance, we could create singlet state. I'm just using tensor network, ordinary tensor network notation from like, you know, spin networks, etc. We can annihilate singlets. We can swap things, we can project onto singlets, and if we build up, for instance, we can put the, we can have a Dirac bispinners to get the Dirac equation, we can have our local Hamiltonian should be Lorentz invariant, so we can do that, we can have enforce those symmetries. It's very flexible, you can do whatever you want. This is the nice thing about this. Why, again, the notion that we should come up with ideas that constrain us to have things like, you know, space-time being 3 + 1 dimensional. Let's not try to solve that problem. Let's just try to get something that works. That's how quantum mechanics works. I mean, as a quantum mechanic, I say that's how quantum mechanics work. Quantum mechanics like me work this way. So let's look at some of the kinds of space-times we get from this. So I'm going to call your attention to this one right here. There's a very interesting space-time which actually is a semi-classical solution where the energy and the times are all 0. It's a stationary point of this action for sure. And this is an interesting space-time because it has no spatial temporal extent. So it's perfectly possible to get regions in this computation where, you know, it looks like it has spatial temporal extent. I drew it as if it's spatial temporal extent, but the actual spatial temporal extent is 0. And this is the first solution I found, and I claim this is a good solution, because there are other solutions like the ones that we see around us, but this is a very nice solution, because it's like, okay, nothing is a solution to the problem of life. Here's what happens when you look at things like, this is a Penrose diagram, Penrose diagram for a black hole for a Schwarzschild solution, a stationary, non-rotating, non-charged black hole evaporating. And you can get things like, if here's the r = 0, here's the horizon, the light-like horizon, here's the space-like singularity, and then you can get things like the Horowitz-Maldacena model for black hole evaporation, in which incoming ordinary matter gets annihilated, and this is the Hawking radiation out here. Positive energy Hawking radiation of parts of the singlet go in this direction, negative energy parts fall in, and in the Horowitz-Maldacena model, which works very nicely in this picture, then the incoming ordinary matter gets annihilated as singlets. See, that's the kind of thing you put in this Hamiltonian here, with infalling Hawking radiation. And that's nice because, as Horowitz and Maldacena pointed out, this means that you can get unitary black hole evaporation. Or I would say, if you look at quantum fluctuations, almost unitary black hole evaporation. So that's nice. And then let's look at some more, because I think I can make, I purposely did not do many slides because I knew this was going to happen. Here's a nice, if I look at the quantum gates in de Sitter space, this is a conformal diagram for de Sitter space. I've only drawn the positive t part of it. This is plus infinity, time-like, space-like infinity, and you see that the conformal transformation on this diagram says, oh, okay, the number of gates is growing exponentially as we go forward in time, corresponding to the exponential expansion of space and time. It's a nice picture. And then I want to draw, the next one is even more entertaining. I put it on its side, and the nice thing about 1 + 1 dimensions is that de Sitter space, the conformal diagrams, the Penrose diagrams for de Sitter space and the Penrose diagrams for anti-de Sitter space are the same, but you just like flip them on their side right here. And so, fun project we're working on right now is if you have again, this is time going up. You note that in the normal feature of anti-de Sitter space is that if I send a signal off to infinity, this is the time-like infinity. The signal, I send a signal to infinity, comes back, and it goes back in a finite number of logic gates here, which is what should happen in anti-de Sitter space. And now it's very fun to try to look at what happens. Can we make an effective, generically make an effective conformal field theory on this boundary right here? Well, just determine what happens there, but it's also the case that everything that happens in here, if you look at it, all events in here are being determined by stuff that happens on the boundary as well. And so it's very interesting to imagine what happens, for me it's very interesting, to see if one can construct something like a conformal field theory on this boundary. Which would be, you know, the 80th CFT correspondence, certainly the original papers, it's invoked as something that happens everywhere, but I seem to recall that most of the things are like 5-dimensional quantum gravity in the bulk with, 15 supercharges and things like that. So I'm not getting it right here because there are too many of them. But maybe this is a generic feature. Yep, thank you. Well, I have this 5 minutes for questions, right? I'm going to take a little of my question time myself to make it the last slide. More opening questions. So can we have topology change, for instance? Well, I mean, I said, well, let's fix the topology to be Minkowski space. But recall that we have this feature that we can have something that's embedded in space-time where many of these regions don't exist. They have 0 spatial extent. So it's actually not implausible that we could, in fact, have a picture like this, where you have real stuff going on here, and what's going on in the supposed void right here is just 0 extent space-time there. Well, that's one way to do it. There might be other ways to do it as well. Can we have closed time-like curves? In my group, we spent a lot of time looking at the quantum mechanics of closed time-like curves. Well, yeah, actually, we might indeed be able to do that. And in fact, I never restricted these proper times to be positive. Okay. So they could actually be negative. So it's quite conceivable that we could imagine things going backwards in time. There are a very wide number of possibilities that one can explore here, and at least from my perspective, most of them are kind of fun, as long as at the end, as a quantum mechanic, we put the pieces back together into a quantum car that actually runs. And then again, I already mentioned that feature of, can we have a conformal field theory on the boundary? So just to make a nod to the people who have only belatedly, almost 40 years down the line, discovered that space-time is a quantum tensor network, and which just seems to happen. Why that Lenny Susskind, we always argue about this. He finally clicked for him. I don't know what happened. Okay, so I'd like to. This is a program. It's not a. It's a well-defined, system of it's quantum computation. We have the Einstein-Regge action. We sum over all possible times. The only variables are the proper times. They determine both what happens in the quantum computation and the geometry. We then determine we then perform a path integral. The semi-classical paths are given by the stationary points of the path integral, and they are matter that obeys Einstein equations. That's pretty good, I think. But of course, there are many, many open questions, and I invite you to talk with me about it.
Thank you for engaging the audience in a very exciting talk. Now we have 1 minute for questions. I try my best. Better.
Now, Seth, I can ask a question. it's not like I'm defending anybody, but the key point in all programs of quantum gravity is that time should not be considered explicit variable.
Right, so this is different than all except this.
Except Seth Lloyd.
No, proper time is your variable.
No, so I'd like to hear more how you respond to those people. And especially I pick out the biambion and low because they use the Einstein-Reggie formulation and they've been doing that for 40 years.
Yeah, I know, yeah.
Yeah, so so I'd like to hear your comment on it. No offense to anyone.
I actually already, you're talking about Renato Lowell's work, right?
Yeah.
Yeah, I already commented on that. So I think because other people have questions, they're... Well, no, it's quite different, I don't wish...
Quantum gravity would not like to see explicit time.
Quantum gravity doesn't care what we do. Oh, but this is a quantum theory of gravity, includes matter, gives the semi-classical Einstein equations with fluctuations around it, so it gives stochastic gravity. And I said, well, let the variables here actually just be these proper times. What's the matter with that?
No, Seth, I like what you did.
Please. Yeah.
So thank you for a terrific talk. Very, very inspiring. My question is quite simple. In your picture, you mentioned Hawking radiation. What is it, black hole evaporation? What actually happened to your circuits? They become smaller, they work?
Oh yeah, and so
how do you envisage
the
the evaporation?
So when you go and you apply this to, in this Horowitz model, the same model, so what happens, you see, you can actually have, in a place where there might be nothing, you could have nothing there or no time, but one thing that could happen is if you create a singlet. If you create a singlet, then because you're obeying the semi-classical Einstein equations, the energy is zero, so it's essentially a vacuum fluctuation. And so then these are exactly Hawking radiation, but these are singlets that are being created outside the horizon of the black hole. And then, there are light lines that fall into the black hole.
I see that, but what happens to the circuit itself? I mean, you have a circuit, a quantum computer. What actually?
Yeah, so the circuit here, actually, if you look at the circuit, I didn't draw the circuit here because it would be tough to do. So the gates get closer and closer and tighter and tighter and tighter and tighter together here. And then beyond the singularity, you have one of these regions where there's nothing. And then at the singularity, everything, all the matter goes away, annihilated as singlets. And then out here, you have Hawking radiation. So down here, this is actually, at the horizon of the black hole, there's no firewall paradox here or anything like that. At the horizon, everything looks kind of normal. Then you have you've trapped surfaces where you can't send information backwards. So all the information is just flowing inward at this point. But then because you have this annihilation as singlets at the singularity, then you get this Horowitz Malazena model coming out in natural fashion.
Next question, please.
What?
Sorry, please.
We did have qubits. I actually suggest for here the simplest thing is to use fermionic qubits. If they're fermionic, you get fermionic quantum computers, and then you use fermionic qubits, and then you get fermions for free without having to simulate them. Of course, you could simulate fermions, but why?
Okay, let me ask my question. I go along with you because I think it's interesting to explore new things, and one should not raise from the beginning barriers and say that will never work. But you decided to have your gravity part to implement it in a way that is not unitary. So you give you some intrinsic irreversibility, that's what you were saying.
I didn't decide that. It turned out to be that way because I could calculate it.
Let me ask on that, because I think first of all you are not forced to. You can of course also implement the gravitational part by just keeping your Hamiltonian Hermitian, keeping the transformation unitary. Otherwise actually it's not quantum computing anymore, because quantum computing has, of course, unitary matrices. Why I'm asking that is once you decide to implement gravity in a way that the Hamiltonian is no longer, the combined Hamiltonian is no longer Hermitian, there is, of course, a big risk that your system will just go to equilibrium after a finite time. Now you can say that Planck time is very short compared to, let's say, the inverse electron mass. That's certainly true. But the universe is very old as compared to the inverse electron mass. So my simple question is, did you ever look if your system will not go to an equilibrium state, and what will be the time scale? Because that's a big danger once you have loss of information because you have no longer unitary transformation.
Yeah, that's a very good question. So if I look at a, so let's see, what's a good picture for this? Well, so the, if I look at these, let's take a very long, a set of many of these, a long time-like path, and let's ask what happens along this long time-like path. Well, the system will obey these, will have these fluctuations, but the fluctuations over this long time-like path will also be order of the Planck length. So I actually think even making the path longer does not necessarily cause everything.
So maybe please.
The small non-unitarity or small
next
non-Hamiltonicity in your combined Hamiltonian, and you go for a long time.
It doesn't work quite that way, right? Because there's no, I have not done a Hamiltonian formulation of the quantum gravity part. I'm doing an action formulation.
The last question.
Yeah, just a quick question about the slide that you were showing. You looked at the stationary action and then you found that the proper times fluctuated the Planck scale, and you averaged over these fluctuations to get a decoherence effect, right?
Yeah, so, but of course nothing, the overall system is still coherent. You're still adding up coherently all these actions. So there's no actual, just in the path integral formulation, you get fluctuations, but the whole system can still be coherent. So I don't even know, I haven't looked at the Hamiltonian version, I don't even know if the overall version is still Hamiltonian. It might in fact be unitary, which would be a very interesting question. I actually take this question as a good one, and I wonder what the answer is. And let me close, because everybody else lost their last slide. I put in the last slide of our neighbors and our farm up in Vermont, and it actually made it through. So thank you guys very much.